First of all, I will try to motivate the talk. There's a setting that you face as a data scientist or data engineer almost every day. And we're going to look at that setting, and to convince you even further, we designed an end-to-end pipeline coming from the healthcare domain in this case, where we want to actually prove it's quite common to interchange data in between deep learning and data science frameworks. When inspecting that end-to-end pipeline, we will identify bottlenecks, usually hardware bottlenecks, and we can address them. Most of that will be done by Miguel. We will talk about memory management. We will talk about how to convert data efficiently, but also how to load it efficiently. And most importantly, if we talk about interoperability, we talk about how to transfer data from A to B. Finally, we will summarize the talk. So let us have a look at motivation first. On the left side, you see three people, data scientists wearing white scrubs. I know that usually data scientists don't wear white scrubs, but a pullover like me today or hoodie. Nevertheless, this is often how we are perceived. In the middle, a CUDA developer, and on the right, a data engineer. So the data scientist most probably will work with well-known frameworks, while the CUDA developer might write low-level CUDA code or implement highly efficient I/O pipelines. The data engineer might try to identify new data, clean data, and gather new sources of data. This is what they do. They have to collaborate on a daily basis, but due to their different latent needs, they might have different preferences for frameworks, and that's completely okay. On the right side, you see a bunch of frameworks. I think the most popular ones are the two deep learning frameworks, TensorFlow and PyTorch. But also you could think of performing some data science tasks, and in the middle you see Rapid. That's actually a GPU accelerated drop-in replacement for Pandas and SciKit Learn. So that would also be a good choice. Let's assume you have tabular data. Or you might be the CUDA developer in the middle and want to implement some low-level CUDA kernel from within Python. And there's a framework for this called Numba. Or you work with numerical data and the CUDA accelerated version of NumPy that's called CuPy. That would be the framework on the upper right. Finally, you could be someone who's working with just-in-time compilation frameworks, such as JAX on the right. So all these frameworks have a good reason to exist, and they excel at certain strengths, and they might have some disadvantages. And therefore, on the left, these people might choose different frameworks, but that means that they are forced to interoperate between those frameworks. And before we go on, let me give you a brief outlook of this talk. First of all, on the upper left, you see a pipeline starting with Rapids QDF, then using CuPy, Numba, PyTorch, and Rapids. This is the already mentioned healthcare pipeline that will be explained in detail. And obviously, this pipeline consists of different frameworks, and therefore we need to interchange data. On the right, you see a graph where we discuss how to do that in detail, and we will also look at that. Miguel will talk a lot about memory management, memory layouts, data standards and standardization approaches. That's on the lower right. And if we have enough time, we will also look at RDMA hardware accelerated features for interchanging data in between devices or GPUs. That's what we do. We prepared source code for that. The whole end-to-end pipeline is written down in a Jupyter notebook, and we can share that. It's linked at the end of this talk and the summary. And I already mentioned that we will discuss how to actually convert data from one framework to another, and we provide a nice convenient table. You can see it on the upper right. That's also part of this talk. But let's start. Let me convince you that you actually need several frameworks and that it's not enough to just have one. This will be a healthcare related task, and we will have 20 hours of continuously streamed ECGs, so basically heartbeats. But we have no segmentation, so it's just heartbeats measured 20 hours in a row. It's univariate, that means scalar, so not vector valued, and uniformly sampled over time, so we have a fixed length of time steps all the time. On the left, you see a prototypical heartbeat. Cardiologists tend to annotate those submotives with letters P, Q, R, S, and T. We will not really need that for the rest of this talk. Nevertheless, I will sometimes refer to certain shapes in our signal by P, Q, R, or S. So don't wonder if I use letters to point at things. What we will do, we have this long stream of time series data, and we will segment it into 100,000 heartbeats in an unsupervised manner. Having 100,000 heartbeats, we will train a variation autoencoder for both outlier detection and also for generating new data. So we could generate new heartbeats. And of course, since we are generating new samples, we would also like to visualize them. Here's the disclaimer. This is an end-to-end pipeline that was not verified in clinical routine. So please don't use that at home to diagnose heart diseases. Leave that to the experts, please. Okay, let's start. So you would probably argue that when someone gives you hours, even hundreds of hours of ECG data, that should be stored in a efficient format, like could be netcdf, HDF5, but often it's not. Let's face reality. Or usually, as a data scientist, someone just enters the room and gives you either a link to Google Drive or a hard disk with terabytes of CSV files on that, right? Many people do not know that parsing floating point numbers stored in ASCII format is actually quite expensive. And therefore, this can already be a bottleneck. Usually when you would read that data in, you would use the CSV reader from Pandas. Here we decided to directly use the Rapids QDF IO submodule, and Rapids QDF is basically Pandas on the GPU, already accelerated. Here the advantage is that this reader will not only parse the data on the GPU, but it will also directly store it in GPU memory, which is significantly faster than CPU memory. The result will be a data frame that you see on the right. If you print it in a Jupyter notebook, it looks exactly like a Pandas data frame, just that it lives on the GPU. Okay, we have the data in GPU memory, that's great. But now we face the fact that it's continuously measured data, and there is no segmentation. We do not know when a heartbeat starts and where it ends. So our job is to actually segment it. And here we use an unsupervised approach by basically convolving a heartbeat with a wavelet. On the left, you see a graph. The blue signal is actually a full heartbeat, and the orange signal is a so-called Ricker wavelet, which is more or less the second derivative of a Gaussian. Here we chose that the standard deviation of that Gaussian is more or less the same as the width of that QRS complex. I said it, I will use the letters, right? That is this submotive in the dashed box. By doing so, we can more or less compute the output of that filter, which more or less measures where is this QRS complex. And on the right side, you see it, the long continuous measured signal in blue, that are the heartbeats, and the output of this filter. Please note that in the signal, you see some temporal drift in the average of the values, because when measuring heartbeats using electrodes on a human body, for example, the patient could either move or be sweating, and therefore the resistance changes, so also the voltage that you measure changes. And this is here actually a challenge, because amplitudes and moving averages might change. You already see that the filter, when applying here the wavelet, is a little bit agnostic to that, right? It will kind of forget this drift. On the other hand, it's not completely blind for amplitudes. So when we want to know where a heartbeat begins, our job would be in the right plot to identify the maximums, the local maxima in that plot. And how would you do that? You would probably use a tool, but let's conclude this slide first. We needed to perform that convolution using a Fourier transform in CuPy, which is more or less NumPy on the GPU. But this is not the RapidsQDF framework anymore. Therefore, we needed to copy the data from one framework to another, and this should be efficient. I already said that we are interested in those local extrema, and there is an algorithm for that called 1D non-max suppression. Unfortunately, CuPy doesn't have a sophisticated 1D non-max suppression algorithm, so what can we do? We could potentially implement it on our own using CUDA. Here we use Numba as a just-in-time compiled CUDA library that allows for writing actually CUDA from within Python. It's really great, and later you will see that it's even well integrated in the ecosystem. We will do that. When we do that, again, we need to copy data from CuPy to Numba, and that could be inefficient if we don't do it right. Having such a 1D non-suppression algorithm, what we actually do here, we get a gating function. This is again the orange signal. It's more or less determining where was this peak in the orange signal before, and setting that to 1 and everywhere else to 0, and therefore the gate is exactly 1 when the heartbeat starts and 0 for the rest of the heartbeat. You might also see that those spacing in between the gates is not always the same. That is caused by the fact that heartbeats do not always have the same length. And here our job would be to actually extract them all and to embed them in a fixed length data matrix. You see that on the right. Here we even apply normalization of amplitudes and averages to make it even more fancy. Nevertheless, our proposed algorithm works quite well. You see that all the signals align at the QRS complex, which is good. Again, we needed to copy the data. Again, we needed to write a kernel even, which is not related to numerical processing known in CuPy or QDF at all. So a completely different framework copying of data was necessary. Now that we have the data matrix of fixed shape, 100,000 heartbeats, we can train a variational autoencoder. There are many variants of that. Here we use basically the vanilla variational autoencoder as proposed by Kingma in his PhD thesis. The job is actually to compress data using an encoder here called Q of Z conditioned on X, where X is the input data. And we decode it again with a decoder called P of X conditioned on Z, where Z is exactly that latent space in the middle. Looks very much like a standard autoencoder, with the difference that the variational autoencoder will try to align the points in the latent data in the latent space with a prior probability distribution, and the most easiest one to implement is a Gaussian. Here we chose a 2D Gaussian to map the latent space, and therefore every point in that plane, in that scatter plot below, belongs to a heartbeat. And if that they are actually crosses, if that's in the middle of the Gaussian, so it's a very likely heartbeat under the training set. And if it's at the margin in the outer regions, then it's an unlikely heartbeat. Having that, you can perform outlier detection. That's great. You could say, okay, this heartbeat is not very common under the training set. Or you could even, and that's the most fun, make up new points in the plane and just use the decoder to get new heartbeats. Again, I don't need to repeat it anymore, but in order to train a model in PyTorch with data coming from Numba, we need to convert data from A to B. Finally, you might want to visualize your data. We do this here with RapidsQ cross filter. You see again on the left the latent space, on the right the output of the decoder. Here we see 9 heartbeats, and with coordinates in the title, the coordinates are actually the coordinates from the latent space. And if you, for example, take the last row, the column in the middle, 0.1, minus 0.6, this is an unlikely heartbeat, and actually it looks a little bit strange compared to the others. So this is a pipeline, and this could be used, but as we are human beings with our preferences, we could try to even alter this pipeline. The most, let's say, obvious choice would be to use another deep learning framework. Could substitute PyTorch by TensorFlow or MXNet or Chainer. But you could also say, well, look, I really like GPUs, but for whatever reason, I want to use Pandas for reading the CSV. files, so you could use Pandas at the beginning, or NumPy for the global convolution using the Fourier transform in the second step. That's all possible. And of course, you could use different visualization frameworks. So here we see at least 5 end-to-end pipelines on that slide. And the question would be, are they efficient? And how can we see that they are efficient? And you might already guess that the more green there is, the more NVIDIA libraries, probably it's more efficient. But let's talk about how to convert the data in detail. Here you see a graph where the nodes are represented by green boxes or blue boxes. Those are the frameworks, deep learning or data science frameworks. And then you see edges in between the nodes, either green or black. And those are the conversion paths in between those networks. And whenever it's green, we can actually copy data from a GPU framework to another GPU framework, and even more interesting, using a technique called zero copy. So we're not actually copying the data at all, but just passing more or less the pointer in the video buffer. So we can basically keep the data where it is, which is actually the most efficient way. Whenever you have a black box, it means, a black edge, it means that potentially there might be a full copy involved. That we cannot just pass a pointer, or between a blue and a green node, that these frameworks live actually on different architectures like a CPU and a GPU, and therefore copying data in between them would involve slow PCI Express transfers. And this is really slow, right? Even if you have a PCI Express version 4, you would end up with effectively 24 gigabytes per second, which sounds like a lot, but keep in mind, passing data on a GPU can be done at 3 terabytes per second on a Hopper GPU. So 3 terabytes versus 24 gigabytes, I would favor the GPU in that case. Okay, and this is all I wanted to say for the introduction. And here I actually ask Miguel to continue with memory management, and I would drive the slides.
Thank you, Christian. So before starting, please let me mention something that I think it's well worth, because Christian highlighted that there are multiple ways to do the same thing, and that's correct. But one of the things that I usually face while meeting customer or users is that they have a bottleneck somewhere in their pipeline. So how do I usually assess them to try to overcome those pipelines? So the first thing is just to profile your application and try to understand which is your bottleneck. Is it just loading the data? Maybe, and as Christian will describe, you can use a GPU accelerated version of a reader for CSV file, Parquet files, or others that skip the CPU or the PCI Express. And that's all. And then your end-to-end finishes, and it's great in terms of performance. Maybe you want to invest more time optimizing the remaining steps, and that might be reasonable, but maybe because of just business implications, it does what it needs to do in a reasonable amount of time, and you cannot invest more engineering time to keep on improving your pipeline. You just stop there. That's fantastic. That's what interoperability means also, to be able to mix and match not only software, but also hardware. I always say GPUs are great, CPUs are great, DPUs are great. Any piece of hardware that we have available for us, it's great. We just need to make the best of them. Okay, I wanted to highlight that because this talk is about identifying also potential bottlenecks and how to overcome them efficiently, having also into consideration our daily lives. Sometimes we cannot allocate as much time as we would love to solve a problem in a perfect way, but maybe a non-perfect way is also a reasonable solution, and that's something I would like you to take with you. I do that in a daily basis, basically. So Christian, if you can please move the next slide. So you probably know this person, okay, Cookie Monster, and his famous phrase, something like "me want cookie" or something like that. Why I have this person here is because I would like to talk to you about memory usage in deep learning frameworks, in machine learning frameworks. So maybe you don't know, but memory allocations and deallocations are usually expensive. Not when you allocate once, but when you allocate hundreds of millions of times while training a deep neural network. That's why there are some technologies like, for instance, layer fusion, which is only wrapping multiple kernels, multiple functions into a single one to avoid exchanging data between them. So something similar happens with memory allocations and deallocations. For instance, if you just to import TensorFlow, the chances are that even if you stored a tensor with just a single element, 70% of your available memory is pre-allocated by TensorFlow. And that can be a reasonable approach, because what they think or what they do is, I will pre-allocate a huge amount of memory, I will do it once, and then I will deal with the memory internally. So I don't need to do allocs and deallocs continuously. I will manage the memory by myself. And that makes sense if you are the only one that wants to use that GPU, that CPU, and that memory. But the thing is that when, as Christian showcased, we sometimes need to make work together multiple frameworks. So if one of them has 70% of the memory, well, what do we have left for the others? And what happens if the second one takes the 30% remaining? So we couldn't use a third library, basically, but without an out of memory. So we started thinking about memory managers in a way. And before moving to that, there are ways to overcome those issues. For instance, if you are pretty sure that you are about to use 3 frameworks, you could say to TensorFlow, to PyTorch, just use 30% of the available memory. That's another approach. But it requires to do some measurement profiling to make sure that you don't pre-allocate more than needed and you don't get short either. So there are other approaches. You can tell PyTorch or TensorFlow, just grow your memory requirements as needed, so on demand. So that could lead to the source of the problems. That is that if you keep on allocating and deallocating memory, that's expensive in terms of computational time. So there are other approaches. Can you, oh, that's fantastic. So the next approach is just to use an external memory allocator, a memory manager. That means instead of letting each of the different frameworks to deal with the memory itself, let's use another library that will deal with the available memory for all the frameworks. And that is Rapids Memory Manager. As Christian highlighted, Rapids is an open source framework that tries to cover the end-to-end pipeline for data scientists. It has lots and lots of libraries like QDF, which is like Pandas, same API, but running on GPUs, QML like SciKit Learn, QGraph like NetworkX, QStringSet, and many others, with the philosophy of first being open source and second, drop-in replacements. So you don't need to change your code. So if you have, for instance, from scikit-learn import random forest, now you have from QML import random forest, and you have random forest running on GPUs already. Exactly the same as we saw before. Instead of pd.readcsv, you can do qdf.readcsv, and you have your data loading running around 25 times faster by only changing the import and using GPUs in that case. So under that umbrella of Rapids, we created a Rapids Memory Manager. That was the library that we decided to use to deal with the data with our internal libraries. But we noticed that it could be extended worldwide, and we open source that. And it is basically a library where anyone who wants to use it needs to implement a couple of methods, allocate and deallocate. And that's all. Once you do it, your memory request will go through the RMM, Rapids Memory Manager, and we won't have those issues, because when TensorFlow needs memory, it won't pre-allocate the data. It will just ask Rapids Memory Manager to provide data to it. Currently, it is already supported by CuPy, Apache Spark, Numba, XGBooks, and there is a pull request which is about to be merged for PyTorch. So far, in the short term, we don't have an integration done with TensorFlow. But the great news is that because it is open source, you don't need to wait to Google to implement that or to us. Just do it yourself. So that's something great. And we will overcome all those problems. Another interesting thing is that having an external memory allocator as RMM, we can do lots of things on top of that. We can do login, we can try and predict memory leaks, we can limit the amount of memory for each of the consumers. So by having that centralized point, we can add more features to what it could be a vanilla memory allocator and deallocator. There is a comment there that with the Rapids, Basically, this is just a silly trick. If you want to use, for instance, RMM with CuPy and Rapids with QDF, for instance, we encourage you to import first QDF, because if we do import QDF and then import CuPy, CuPy will notice that there is already a working version of RMM in memory, and it will make use of it. If we do that the other way around, we need to, if we do import CuPy and then import QDF, then you need to explicitly tell to CuPy to make use of RMM. So as a rule, just import QDF first. That could save a lot of issues. Then data conversion bottlenecks. That's an interesting topic, because when all these frameworks like Pandas or NumPy were first thought or developed, nobody thought about having complex pipelines. So basically, each of them implemented their own memory layout. So how do they store the data in memory? They implemented their own, the most efficient for their specific pipeline. That was reasonable at that moment, because we were using Pandas for almost everything or whatever. But it has also some cons. For instance, if we have a look to Parquet and Pandas, Parquet file format, it stores the data in a columnar-wise layout. We'll see what's that in a few seconds. While Pandas itself used to work with a row-wise layout. So the only process of reading the data from Parquet files to Pandas implies transposing the data. So that's very time-consuming. It also requires extra memory to make it done, so you cannot use your available memory as much as possible. And what it is worse, that copy and converts, that transpose of data doesn't add any value to your business. It's just an internal thing. So, and that happens a lot. For instance, before Spark 3.x, so with Spark 2.x, we had exactly the same problems. It used to deal with a row-wise layout, but the data used to come in Parquet on other formats where it was organized in columns. So no help at all. It is a waste of time, basically. Hopefully, with the Spark 3.x, we can already store the data in a columnar-wise layout. It can also be GPU accelerated, so we don't have those issues anymore. So how to solve this waste of time? So if you can please move to the next one. So what Rapids did, and many other people did, is to adopt a standard to organize the data in memory. So there is one standard, which is Apache Arrow, which is a specification where it details how the data should be stored in memory. That's all, regardless if it is host memory, CPU memory, or device memory, GPU memory. It doesn't matter, okay? And by having the data organized the same way, when we want to make two libraries interact among them, we just need to pass a pointer to the data, because the data doesn't need to be transformed to be readable by other libraries. So we already have a really good starting point. So we adopted Apache Arrow. Apache Arrow itself specifies that the data should be organized in columns. Let me show you in the next slide why it requires to be organized in columns. So for instance, on the left, we have a data set organized in rows. So we can see that the user ID, and then we have the timestamp, then we have the source IP, and that repeats on different rows. And on the right, we have the same data in columns. So why do we say that for most of the tasks, not all of them, but for most of them, a columnar layout is better for this kind of workloads? So basically, imagine that we need to do something as simple as calculating the mean of the timestamps in this small data set. If we want to do that in a row-wise data layout, we need to perform different memory readings, each of them for each of the different rows. So that's time-consuming. If we compare that with a columnar data layout, we can read all the timestamps at once, because they are together in memory, and that makes it more reasonable in terms of hardware to be read at once. And then we just need to calculate the mean. So just reading the data itself would be much more efficient. And it's exactly the same when we are filtering, when we are sorting, and a few other operations. Definitely, you can tell me that there are operations that are row-wise, and you are completely right about that. The great news of interoperability is that imagine that you are performing something on GPUs, and there is an operation that intrinsic itself, like ilog operations, for instance, in Pandas. They behave better on rows, on CPUs, for instance. Nothing happens. There are lots of ways to take a data frame which is in GPU memory. We just need to say to Pandas, data frame to Pandas, and it will copy the data to the CPU, to the host memory. You can then execute whatever you want on a CPU, and at that moment, move the data back to the GPU. So mixing and matching technologies and frameworks, it's good. It's okay. We don't need to stick to something that doesn't provide the best solution to you. Let's be creative and use that. Being fair, well, GPUs historically deal really well with columnar data because we're able to spin lots of processes in thousands of kernels in parallel with regards to a CPU, for instance. But being fair, CPUs introduced a while ago the single instruction, multiple data instruction set in CPUs. So they can already deal efficiently with data organizing columns, which is great because if we are moving the data, we don't need to, we just need to copy the data. We don't need to perform a next operation to transpose or similar to have it available on GPUs. So it looks like a columnar layout is interesting. We adopted Apache Arrow as most of the community did, and it also has some benefits. For instance, next one, and next slide, please, Christian. For instance, there are other representations of the data that are kind of compatible with Apache Arrow. We have DLPack. DLPack is a specification that was meant to exchange data between deep learning frameworks, but it can also be done with NumPy, with Pandas. So basically, it lets you taking a CUDA array interface or a NumPy array interface or just an array and produce a tensor in an efficient way. The great news is if your original data is using Apache Arrow, creating a DLPack capsule, it is named, from Apache Arrow is just slightly changing the headers of the data. We don't need to modify the data itself, just the header. So we're exposing the same data in a different way. And that is, it takes nanoseconds to be done. So we can see on the right that it is quite straightforward. For instance, on the top, we have a QDF data frame on GPU memory. And then we want to create a CuPy array from that. So we invoke from the data frame to DLPack, and in the CuPy, we do from DLPack. That's all. We are using an intermediate protocol, because we are not converting the data, to exchange the data between both. That is zero copy. We don't need to transform it. It takes 0 seconds and it just works. At the bottom, we can see that even if we try to adopt all the libraries, the same method names, we are almost there. But for instance, in this case, CuPy, when they are exposing to DLPack, they don't have the same lowercase nomenclature. So we can see that there. So that happens. We are moving to that direction, and I will speak about some initiatives that will help with that. Okay, so we are much closer. But DLPack, the second format that we will use. Actually, Apache Arrow itself, in many cases, you won't manipulate it yourself. It will be under the hood, but you will very explicitly convert to DLPack or to the next one by using Python or C++. In the next slide, please, Christian, we will see another specification, which is the CUDA array interface. CUDA array interface is also compatible with Apache Arrow. So that means that we don't need to do conversions of the data, as I mentioned before. It is based on NumPy array interface. And basically, it is accepted by many frameworks. Why I'm explaining or we are talking about these different formats, because maybe your target doesn't accept a specific data format, but for instance, and I'm just guessing, and this is not correct, but imagine that CuPy doesn't accept, which is not correct, DLPack. But it accepts CUDA array interface. So we can move from PyTorch to CuPy via CUDA array interface, and then from CuPy to QDF via DLPack. And it doesn't matter because those transformations will be zero copy. So they will take literally nanoseconds to execute. So it's not consuming at all. So this is another specification, also compatible with Apache Arrow. It is already accepted by many deep learning frameworks like JAX, TensorFlow, PyTorch, Numba, CuPy. Just another option that is available for you. And in many cases, you even doesn't need to know what you are using. So for instance, in the next slide, we have an example two methods. At the bottom, we have a Python method, which is segment number, that if I am correct, it returns a CuPy ND array. So it returns data in the CUDA write interface format, but under the data type, which is ND array. And then at the bottom, we have another method, which is segment kernel, that it will need as input device ND array. And we are just passing the data without any transformation. Why? Because both ND array from CuPy and Numba device ND array both accept CUDA write interface. So even if you are passing a specific object, because that object is also compatible with CUDA write interface, you can pass it between the different methods or two different libraries. Let me mention one more thing. Have you seen that there is def segment kernel and you have some Python code? But then we have a decorator, which is CUDA just in time, CUDA.jit. That is Numba. Basically, we just need to decorate the functionality, and in just in time, the first time that this is executed, it will be compiled into efficient C++ CUDA code. So in order to code for GPUs and to have that code running on multiple GPUs and multiple nodes, you don't need to be a C++ developer. And that's a really, really interesting thing. So I think next one, maybe, Christian? And let me talk about this. Is really interesting, and let's start with the joke at the bottom. Okay, so we have 14 standards. Let's create a 15th standard. So if we have Apache Arrow and we have DLPack and we have CUDA write interface and NumPy array interface, why do we need data API? So basically, because we are closer. Okay, but we need to have, and with we, I mean all the contributors to these libraries, we need to agree on a specification or just naming the methods. As we saw before, 2DLPack can be expressed on multiple ways depending on the way your nomenclature rules. So we need to agree on that. And data API, it looks like it is really successful because it was just grouping the main actors in the open source community. Let's discuss an agreement on how to store the data, how to name our methods. And it started in 2020. It looks good because they already published a first specification. It is being implemented. NumPy, CuPy, and a few others already implements that first standard. And as the joke says, once we have it implemented by all of us, someone will invent a new standard and we will be back again. But at least we are moving together, which is good. So that is a consortium that we can use. By the way, I'm not sure if someone shared with you, but we have a GitHub repo with all these slides and code available for you. Our LinkedIn is there. You can reach us if you have any questions. And I don't know if there are more slides, please, Christian. I think that Christian can explain this much better than me. He will talk about data loading bottlenecks. So thank you, Christian.
Thank you, Miguel. Well, let's have a look at a certain experiment. So this is hardware topology. We see buses, how typical hardware components communicate. We see an NVMe drive. This is potentially where our data is located. We see a CPU and we see a GPU. So usually when you would copy data from a hard disk to a GPU, the following would happen. You would copy the data to the RAM attached to the CPU, and then would, in a second phase, copy the data via PCI Express from the RAM of the CPU to the video buffer of the GPU. Why do you need to do that? It's actually because when we started to design GPUs long ago, and also other hardware vendors designed their memory spaces, they all decided to have their own memory space. And technically speaking, memory attached to GPU or memory attached to CPU is different memory and therefore could live in a different memory space. I don't argue with that. Nevertheless, both of these spaces would start with 0. And therefore, if I would give you an address, you wouldn't be able to tell whether it lives on a CPU or on a GPU. We changed that with unified virtual memory addressing by partitioning the global address space into disjoint parts, where certain parts belong to the CPU, certain parts to the GPU. And therefore, if I give you an address, you know where it belongs, whether it should be copied to a CPU or a GPU. And this is a good constrained to allow for something which is much more efficient. Because if an NVMe drive knows that address and it can distinguish without involving a CPU that this data should be copied to a GPU, then when both being attached to the same PCI Express bus, why should they at all involve the CPU, right? They could just interchange data directly. The technique under the hood is called RDMA. We at NVIDIA branded the technique from accessing NVMe drives to GPU memory as GPU direct storage. So that is a good thing. You could fully avoid that one copy into the CPU RAM. And again, CPU RAM is not that fast compared to GPU RAM. So whenever you can, try not to involve a CPU. Here we have an example on how to load CSV data using Rapids. And you could do very similar things like copying via the CPU RAM in the very naive manner as discussed, or using mmap routines, or using GPU direct storage as I just explained. And here you see the performance of those different I/O routines using different amounts of GPUs. And let's have a look at the slowest one in terms of throughput per second. This is a naive one, and this is a constant. This is the green graph at the bottom. And what does this mean? That would mean that your throughput per second stays the same, independent of how many GPUs you use. But that's actually bad news, because that means if I use 8 GPUs, I only have 1/8 of the bandwidth compared to if I would use 1 GPU. Ideally, you would like this graph to be a straight line, right, with a slope of 8. And the best you can get is GPU direct storage. This is the blue line, basically more or less almost scaling perfectly with the number of GPUs. And therefore, whenever you can have RDMA or GPU direct enabled routines to load your data, please do it. It can make a huge difference, specifically in nodes where there is just a few number of CPUs and a huge number of GPUs, right? Because you do not want to be bottlenecked by CPUs if you just spend lots of money on many GPUs. But let's have a look at the setting when you have more than one GPU in a system. Again, let's assume that both of the GPUs are attached to the same PCI Express bus. In the naive setting, the following would happen. We want to copy data from GPU 1 to GPU 0. In a naive way, we would have to copy it to so-called pin memory. That's more or less memory that cannot be paged to disk, living in CPU RAM. Then the CPU would decide, oh, well, obviously you wanted to copy this to the other GPU, so let me send this via the PCI Express bus, and this would happen, right? And then we would have copied data from GPU 1 to GPU 0. Again, when we have this pointer, we already know by knowing the target address that this will live on the other GPU. We can decide that without the CPU and both of the GPUs are attached to the same PCI Express bus, then we could do the following, right? We could just copy the data directly without having the intermediate copy. That saves lots of time. Specifically, that traversing the PCI Express bus is slow. I already said that PCI Express 4 is operating at 24 gigabytes per second. So here we can basically halve the time for copying the data just by eliminating one of the copies. But now let's think even bigger, having two servers with multiple GPUs, and we want to copy data from one GPU attached to one server to another GPU attached to a different server. And you already guessed it, the naive way how to do it can be quite cumbersome. So we start copying the data to the RAM of the CPU. Now, since we need to reach to another server, we need to involve an InfiniBand or Ethernet device. And therefore, we need to copy the data into the driver buffer of the InfiniBand NIC, copy it via the network into the driver buffer of the other network device, now staging it in pin memory of the residing in the RAM of the CPU, and finally copying it via PCI Express to the target GPU. And those are 5 copy operations. And you already got it, right? If only the InfiniBand network device would support RDMA or GPU Direct, then we could do that completely without involving any of the intermediate buffers. And that's what we intend to do. Now we have 5 copy operations, and now let's have a look what happens if you use NVIDIA GPUs being attached to NVIDIA networking or Mellanox InfiniBand devices. We can basically take the data and copy it directly over the network, over PCI Express bus, directly to the target GPU. One copy operation. And this is more or less 5 times more efficient in terms of how many copies you need. Here, let's maybe have a look at it in an even more abstract manner. Exactly the same setting. We want to copy from one GPU to the other. And in the middle, there are the InfiniBand devices. Now they are called DPU, Data Processing Unit. And what we did, we actually took an InfiniBand network device and attached more or less an ARM CPU to it, so that we can offload certain tasks to the network device that's now a data processing unit, right? Because it cannot only send and receive data, it can also process it. And then you could, for example, decide that in the middle, the link in between the two servers could be fully encrypted in a fully transparent manner. And this is important in a multi-tenancy setting. Let's assume you have a data center with different users working on that, and they should not be able to access the data. You could physically go into the data center and just recable it. That's very expensive and time consuming, and most probably you're not allowed to even enter the data center. But a good alternative is just to encrypt all the traffic in between the nodes of the same user. And this could be achieved with DPUs. Again, the recipe is clear. NVIDIA GPUs together with NVIDIA networking, that's something which allows for using GPU Direct RDMA, which gives you the additional speed and even the functionality, for example, to encrypt your data. Let me summarize what we have seen today. Interoperability matters. And I hope we convinced you with the pipeline or with the many examples that we showed that one framework is not always enough. There's always a framework better suited at a certain task. For example, if I want to implement a CUDA kernel, I have a very hard time to do that in PyTorch. Why not just using Numba and ingesting via the CUDA device array interface? Complex workloads are often composed of many libraries. Maybe here we overdid it a little bit with 5 libraries, but I believe 2 to 3, or maybe even 4 libraries in an end-to-end pipeline could be very common, especially if you want to visualize the data efficiently, which we haven't talked about it in detail. We discussed different ways how to achieve that under the hood, Apache Array, and then DLPAC and the CUDA Array device interface as a mechanism leveraging Apache Arrow, and I also wanted to convince you that copying less is always good. We have seen that in the RDMA section as well as in the conversion section, but it's even better if you don't have to copy data at all, right? If you only need a column from a data frame, could perfectly just take the pointer and pass it to another framework, and that's so-called zero copy. Memory management is important. We didn't overstress that, but even allocations and deallocations are expensive. Therefore, having a memory manager in general is good. And having different frameworks, you might have different memory managers, and therefore it's a good idea to somehow provide a mechanism to unify that approach to only have one memory manager. That's also discussed. And in the very end, I showed you that bottlenecks can be overcome with hardware functionality. If you liked this talk, we actually wrote a blog, a series of blogs even, discussing any of the discussed aspects in part 1, 2, and 3. We also recorded this talk for the GPU Technology Conference. So if you want to hear it again and us having different clothes on in that video, just have a look at this link. We provide all of the Jupyter notebooks that we discussed. We didn't go into any implementation details, only exemplary for how to pass data. Have a look at it, it's nice. And specifically, if you're interested in how to convert data from one framework to another, we have this nice table which gives you the commands so you don't have to Google it. And that's all that I wanted to show today. One more thing. Do you want to talk about this, Miguel?
Yes, definitely. Why not? So basically, just very briefly, to give you a few minutes for question, is that we have at NVIDIA lots of resources. Many of them are open source and available for free. And in many of them, you only need your email address or even none of them. How can I start? For instance, NVIDIA Inception, if you are about to create a startup and you need some support in terms of hardware or resources, you can try and reach us on that. We have higher education programs that basically we put available all our courses and content to universities to allow the professors to teach that content. Sometimes we do things together, but camps, hackathons, courses in general. The Deep Learning Institute is another resource where we can where we have different types of courses. For instance, we have self-paced from 2 hours to 8 hours, or instructor-based, which has a really nice thing. For instance, if you may need an expert in financial services, classical machine learning, and you are in EMEA, the chances are that I would be your instructor, because those are my two. My vertical would be financial services, and my horizontals, one of them is machine learning. So we'll have an NVIDIA instructor and a few teaching assistants also from NVIDIA that will go in detail to discuss your issues or following a course structure. And maybe in the next one slide, sorry, we can also, as a summary, we have hundreds of frameworks. I'm pretty sure no one at NVIDIA knows all the libraries that are available. The great news is that they are there to use, and we have many resources. So just follow those links if you would like to learn more about the community. We work very closely with Microsoft in many of these initiatives, so very likely that you can find those links also at Microsoft homepage. And I think that's all. And I'm not sure if there are any questions or something you would like to comment on this.
Thank you very much. Sorry, Miguel. Not Miguel. Christian, you want to say something?
I just wanted to say that I will stop sharing the screen, and
okay.
Happy
Perfect.
to answer questions if there are
any. So it was a lot of information we received. To be honest, it was not the easiest session. Right? You went quite in detail and a lot of things, but I think it was very interesting to also get that information. I think also with the last slides you shared with all the SDKs that are available, and I saw also a lot of on-demand videos, I think, for who wants to go more in depth or wants to see more details about what you guys are all doing at NVIDIA. I guess that's a great place to start off from.
Yes, and we noticed yesterday that lots of developers are not aware of the services that you offer. So it was very good to see that last 2 slides again.
Indeed.
It was a pleasure. I mean, if we had to conclude it, GPUs are an excellent device to perform machine learning as well as data science. It's usually significantly faster, and we, as NVIDIA, we embrace the developer community as well as providing the libraries which allow for the seamless interaction of those libraries.
Yeah, exactly. Thanks a lot for your session. Really great.
Thank you for having us. See you next time.
All right.
Thank you.
Have a nice day.
Have a great day. Bye-bye.
Bye-bye.